How do Maxwells for equations elegantly describe electromagnetism? Imagine a world where electricity and magnetism are not separate forces but parts of a single, seamless fabric. That's what Maxwells for equations reveal. They connect electric and magnetic fields into one unified picture. These equations explain how charges and currents create electric and magnetic fields. They also show how changing fields influence each other, leading to waves that travel through space. This is the foundation of how wireless communication, radios, and even light work. The first equation, Gauss's law for electric fields, tells us that electric charges produce electric fields. Positive charges push field lines outward, while negative charges pull them inward. This helps us understand how capacitors store energy and how static electricity builds up. The second, Gauss's law for magnetism, states that magnetic poles always come in pairs. Magnetic field lines form closed loops without beginning or end. This explains why we cannot isolate magnetic monopoles, and it's key for designing transformers and magnetic materials. Faraday's law of induction explains how a changing magnetic field creates an electric field. When magnetic flux varies, it induces a voltage in nearby conductors. This principle powers electric generators and transformers. The last, Ampere-Maxwell law, shows that magnetic fields are generated not only by electric currents but also by changing electric fields. Maxwell added the idea of displacement current, which allows electromagnetic waves to travel through space without a physical medium. This is the key to understanding how radio waves, light, and microwaves propagate. Together, these four equations form a loop. A changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. This cycle produces electromagnetic waves that move through space at the speed of light. In electrical engineering, these equations help us design antennas, transmission lines, and optical fibers. They guide us in understanding how signals travel and how devices interact with electromagnetic fields. By expressing these laws mathematically, engineers can solve real-world problems involving how fields distribute around objects, how waves propagate, and how materials affect electromagnetic behavior. Whether designing a radio transmitter or a fiber optic network, Maxwell's equations are the blueprint. They unify electricity and magnetism into one elegant theory that explains the behavior of all electromagnetic phenomena. This understanding is what makes modern electrical technology possible and drives innovation in communication, energy, and electronics.